Basic trig identities. We've already seen the reciprocal identities where the cosecant equals 1 over the sine, the secant equals 1 over the cosine, and the cotangent equals 1 over the tangent. We'll be looking at a number of other trigonometric identities. An identity is simply a statement which is true for all acceptable values of the theta. Two more identities, the quotient identities. We have that the tangent equals a sine over the cosine, and of course since the cotangent is a reciprocal of the tangent, it would equal the cosine over the sine. I'd like to do a quick demonstration so you'll see why these statements are true. First, recall that using right triangle trigonometry that the sine of theta equals the opposite over the hypotenuse. Remember the saying SOHCAHTOA that we use to remember these. And now also the cosine of theta equals the adjacent over the hypotenuse. Now what I'd like to do is form the ratio of the sine over the cosine. So over here, sine over cosine would equal, you see we have a fraction over a fraction. Now, of course, it's true that when you're taking a fraction and dividing it by a fraction, you take the fraction in the numerator and you multiply by the reciprocal of the fraction in the denominator. So the reciprocal of that would be hypotenuse over adjacent. Well, looking at those fractions, the hypotenuse will cancel out. We're just left with the opposite over the adjacent. And recall that opposite over adjacent equals the tangent. So we've just shown here that the tangent of theta equals, or was derived from, the sine over the cosine, which verifies this first statement. Of course, we don't have to separately verify the second one because we've already learned that the cotangent is just the reciprocal of the tangent. Here we'll do an example of a quotient identity, applying a quotient identity. Alright, we've got that the sine of theta equals 3/5 and the cosine of theta equals 4/5. Let's find the tangent of theta. So from the previous slide, we have that the tangent of theta equals the sine of theta over the cosine of theta, and plugging in these values we're given, we would have 3/5 over 4/5. So to divide this, to simplify it, we take the 3/5 and we multiply by the reciprocal of the denominator, 4/5, which would make it 5/4. These 5's will cancel, and so therefore our tangent of theta equals 3/4. An easy problem to solve, provided we knew that last identity. Okay, here we're going to look at, well actually I'm going to demonstrate for you how we can get a Pythagorean identity. A Pythagorean identity is an identity that comes as a consequence of the Pythagorean theorem. So if we look at this triangle here where our legs are a and b and our hypotenuse is c, we know that a squared plus b squared is c squared. That is the Pythagorean theorem. Now what I'd like to do here is I'd like to divide by the c squared and see what the consequences are of doing so. We know mathematically if you do it on the right, you have to also divide the terms on the left by that c squared. Now this first fraction, a squared over c squared, that could be written as a over c squared. The second fraction could be written as b over c squared. And notice the third fraction, of course, equals 1. Anything divided by itself is 1. Now let's look back at the illustration. Notice I've identified the angle theta here. And so A would be the opposite of that angle, B would be the adjacent, and C would be the hypotenuse. Well, then this first fraction here, A over C, that would be the opposite over the hypotenuse. Now we know opposite over hypotenuse is the sine. So this would be sine of theta, and it would be squared. Now you probably expect me to write a parenthesis around this and then put squared. It's customary in trig to instead put the squared sign right after the three-letter abbreviation. So this is read sine of theta squared or sine squared theta. The next expression here, b over c, if we look at the diagram, we see that that is adjacent over hypotenuse, and that means cosine. So we want cosine squared theta, and again it's customary to write the squared here after the letter cos. And we have equals 1. And this is a Pythagorean identity. And we'll apply it in just a moment. There are two other Pythagorean identities you can get. Notice up here in the derivation I decided to divide all three terms by c squared. Well, I could also redo it and divide by a squared all three terms. I could also do it a third time and divide all three terms by b squared. You're going to get the second and third identity on this page if you follow those other steps. So these are known as our Pythagorean identities. Notice the second one, 1 plus tangent squared is secant squared, and the third, 1 plus cotangent squared equals cosecant squared. And of course, let's apply this to an example. Let theta be an acute angle. So in other words, it's just one of the two angles in a right triangle, other than, of course, the right angle itself. Furthermore, suppose that the cosine of theta equals the square root of 2 over 3. Find the sine of theta. Well, we now have an identity that will allow us to do that. The identity we're going to use is sine squared theta plus cosine squared theta equals 1. Notice we want the sine, so we want that first term. It's sine squared, but we want sine. But we do know the value of the cosine already, so let's just plug that in. We'll have sine squared theta plus, and now cosine is square root of 2 over 3. We were given that. Of course, it's squared. And then we have equals 1. Well, let's just trace through the algebra here. When we square this fraction, when you square the square root of 2, you get 2. When you square 3, you get 9. I'll now subtract 2/9 from both sides. And I'll have sine squared of theta equals, now 1 would be 9/9. So 9/9 minus 2/9 would be 7/9. Now that gives us sine squared, not sine. So what we'll do next is we'll take the square root on both sides. That'll give us sine of theta. And on the right we'll have the square root of 7/9. We can separately write the square root over the numerator and denominator, which will allow us to square the denominator. Square root of 9 is 3. There we are. One more topic we're going to look at in this lesson. In mathematics, complementary angles are angles that add to 90 degrees. And in any right angle, such as the one shown, since we have the right angle shown, the other two angles have to add up to 90 because all three of them have to add up to 180. So for instance, if theta here were equal to 20, then the other one would be 90 minus 20, and it would be 70. So 20 and 70 would be an example of two complementary angles. All right, now I'm going to do a little demonstration for you here. Let's talk about the sine of theta, which is the upper right angle. Now the sine would equal the opposite, which in this illustration would be b, over the hypotenuse, which is c. Now what I'd like to look at would be the cosine of the other angle, which is 90 degrees minus theta. If we're now looking at this angle, the cosine would be the adjacent to that, which would be B, over the hypotenuse, which is C. And please notice that both these expressions were B over C, so both these expressions are identical. We can summarize that by saying that the sine of theta will equal the cosine of 90 degrees minus theta. And this statement will always be true for any acute angle. If you take the sine of an angle and the cosine of a complementary angle, they will be identical. For instance, if we had the sine of 30 degrees, it would equal the cosine of what angle? Well, the sine and cosine, technically what we say is that they are cofunctions. And when you see the co part of the word cofunction, think complementary angle. So the sine of 30 will equal the cosine of 60. Why do we know that? Because 30 and 60 are complementary. That is, they add up to 90 degrees. Please notice that all the cofunctions work the same way. So sine and cosine are cofunctions. You simply take the word co and put it in front of sine. Tangent and cotangent. Secant and cosecant. So with cofunctions, if you apply the one to theta, you can apply the other one to 90 minus theta, and it all works out. I'll write you another quick example here. So for instance, the tangent of 15 degrees. Now the cofunction of tangent, you put the letter CO in front of it, so it's cotangent, tangent versus cotangent, and the angles have to add up to 90. So notice that would make it 75, because 75 and 15 give 90. We could have the same discussion if we replaced with radians if we replaced our 90 degrees with pi over 2. Okay, good luck. That ends this lesson.